So far we've developed the real numbers. We've seen the field properties, the order properties, and the completeness properties, and we've even proved a few things along the way, like 0 is less than 1. That's a nice foundation for this course, but of course things will get very, very slow if we have to stop and prove every sort of basic fact along those lines. And so here we're going to prove a couple of theorems which are going to make our proofs a lot easier, and also sort of let us get rid of a few of these sort of basic details and calculations that get used very frequently. The first is one you've almost certainly seen before, called the Principle of Induction. It's written in a sort of funny way in the lecture notes. We say the following: let S be a subset of the natural numbers which has the following properties. 1 is an S, and for every n in S, n plus 1 is an S as well. And the conclusion of the theorem is, well, every set S with that property is actually the complete natural numbers. How do we actually use that in a proof? Well, we use this the way that you've probably been taught about the method of induction. We're always going to define S to be some set of good integers, that is, the set of things with the property that you're trying to prove. And then how do you do a proof by induction? First you prove the base case, that is, you prove that 1 is an S, and then you do an induction step. You check that if n is an S, then n plus 1 is an S as well. Okay, so theorem 1.9 sort of justifies that proof structure. I'm sure most of you have seen this before, but let's do a silly example. Theorem for all integers n and n, either n is even or n plus 1 is even. Now, usually, since we're all finished elementary school, I wouldn't say what does even mean, but we're doing foundations at the moment, so let's just say for a second, n is even means, that there exists a natural m so that n is equal to 2m. Okay, so that's what I mean by even. Of course, this is exactly what everybody means, but it's nice to sort of write down a careful definition since we're being so careful for everything else. So how do I prove something like this? Well, I'm going to use the principle of induction. Like I said, the first step is to say what your set S is, and it's a set of integers so that either n is even or n plus 1 is even. So it's a set of integers that satisfies the property that I'm interested in. Then I do the base case. The base case is even, easy. I want to check that 1 is in the set. In other words, I want to check that either 1 is even or 1 plus 1 is even. And obviously 2 is even, right? Because 2 is equal to 2 times 1. So 2 is even, so 1 is an S. Great, so I've done the base case. Now I want to do the induction step. I want to check that, that if n is an S, then n plus 1 is an S. And there are two cases to think about. The first case is that n was an S because n plus 1 is even. Well, then I'm done, right? N plus 1 is an S. That's all I needed to check. The second case is that n was even, but I don't know if n plus 1 is even. Well, what can we do? In that case, n is equal to 2k for some k in n. That's what it means for n to be even. So that means n plus 1 is 2k plus 2, which is equal to 2k plus 1. But k plus 1 is an element of n, therefore n plus 1 is even, and therefore n plus 1 itself is an element of S. Okay, so that's a little bit silly. I kept on just adding 1, but of course it's a silly theorem, so what could you hope for? So what have I done? I've checked the base case, I've checked the induction case. Therefore, by the theorem, by the principle of induction, S is actually all of n, and in particular, this property here is satisfied for every natural. Okay, so we knew that, but it's nice to check. There's another principle which gets shown at around the same place in the lecture notes. I'm not going to give a proof, but it's an exercise and one that's sort of worth doing if this sort of thing bothers you. That's called the Archimedean property. Okay, it's hard for me to pronounce that, sorry. So this property is sort of long, but it's going to be used very, very frequently. And it's written here in 3 parts, although you'll see it written slightly differently in different places, because all 3 of these parts are somehow very similar. So what are the 3 parts? The first one really seems silly. For every x in R, there exists a natural number n that's bigger than x. Okay, well, that seems probably pretty believable. For any pair x, y that are strictly positive, there exists an n so that n times x is bigger than y. And given any x in R with x greater than 0, there exists an n in n so that 1 over n is less than x. Well, that's really just the same thing with one of these replaced by the number 1. So C is sort of immediate from B. So these are 3 properties. And what's the point of all of this? So first of all, we haven't proved this, but I think that probably if you've been following the field axiom proofs, then you probably have a pretty good guess as to how to prove this. In particular, this is a whole lot like the theorem that we did prove in class, that for all a less than b, there exists some c's that's between a and b. So this is very short notation, but we proved that in a previous video. If a and b are real numbers with a less than b, there exists some c that's in between. So we proved that before. The proof of the Archimedean property, or at least the parts after the first one, you're sort of playing the same type of game of guessing what the number should be and then checking that it really works. What are we doing when we're talking about the Archimedean property? Well, really what this is talking about how Q and R intermingle. In particular, one thing that we're going to be seeing very soon, based on property C, is if we have any real number x that's a little bit bigger than 0, we can sort of sneak in a rational number 1 over n that's between 0 and x. So in particular, what we're going to see is that the Q is all sort of mixed up all throughout R. There's no way to take a chunk of R and entirely exclude Q from it. Okay, so that's going to be very important throughout most of the rest of the course. I'm not going to do this here, but I would suggest on your own go and try exercise 1.4.7. It's sort of a nice check to see how well we understand what's going on here and how to use this property. Let's carry on. So as I said, one of the points of the Archimedean property was to check that Q and R are all sort of smooshed together. They intermingle a lot. So I need a more technical word than smoosh if we're going to be using that idea in theorems. And the idea that we want is this definition called density. So here's the definition. A set E contained in the reals is said to be dense if every interval AB contains a point of E. In other words, what does that really mean? It means if you take the real line like this, and you want to take a chunk of the real line, that is a little interval, every one of those intervals is going to be containing part of E. There's going to be a little bit of E sitting inside the interval. And even if you make the interval smaller, there's still going to be a little bit of E there. And no matter how tiny you make that interval, there's still going to be a tiny piece of E sitting inside of that interval. Okay. And the main theorem that we have relating to this notion is that the set Q of rational numbers is dense in R. So how do we prove that? Well, we're going to be using the Archimedean property. So we have to be a little bit careful about the order here. If we want to prove that the set Q of rational numbers is dense in R, what we need to show is that for every interval AB, we can find a point of E that's sitting inside the interval AB. So all right, let's think for a second, because we haven't gotten to this type of proof yet in this class. What happens in this type of proof? What I'm really saying, if I want to prove that the set of Q of rational numbers is dense in R, is I want to say, hey, you, sort of my enemy out there, give me a pair AB, and then me, the theorem prover, I'm going to find some element of my set Q that's contained in AB. In other words, when I'm proving something like that, I get to say, hey, you got to give me an AB, and then I'm going to find my element of Q afterwards. If we didn't do that, if I had to sort of find my element of Q first, of course it's easy to find a pair AB that avoids a particular element of Q. So the order really matters. All right. With that little sort of aside out of the way, let's see how the proof is going to go. So the first thing that I get to say is, hey, hand me an A and B. So the way that I normally write that is I say, hey, fix some pair A less than B. And the next thing that I got to do is find an element of Q that's sitting there between A and B. So how do I do that? Well, this picture is sort of what's going on. So I'll try to explain that before I do any of the algebra. Sorry, that A is a little bit hard to read. So I've drawn my A and my B. And even though the A and B can be extremely close, I can certainly zoom in so that they look sort of big. And what the Archimedean property is going to let me do is it's going to let me find this number n so that 1 over n is tiny, tiny, tiny compared to the distance between A and B. Right? So whatever this distance from A to B is, I can certainly find an integer n so that 1 over n is much, 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 much smaller than that distance. And what's going to happen if I look at this sort of A minus 1 over n to A plus 1 over n? Well, I'm going to be able to find some rational number that's sitting inside there, and that's the number that I'm going to want to grab. Okay? Now, in previous proofs where we wanted to construct a number, we often chose a number that was sort of in the middle. You could do the same thing here, but it's sort of inconvenient to do, so I'm not going to bother. So let's turn that into something that's a little bit more formal. By the Archimedean principle, there exists some natural number n so that 1 over n is tiny compared to b minus a. So I chose some number there, 500. Doesn't really matter what that number is as long as you choose something that's reasonably large. So there's some integer n so that 1 over n is much smaller than b minus a, in particular less than b minus a over 100. Similarly, by another part of the Archimedean principle, there exists some other integer m, so that m over n is less than a and is less than m plus 1 over n, right? So that's certainly true, right? So what's going on there? What is this m? Well, let's draw the picture again. I have a here. Let's assume it's not sort of very far from 0. I'm going to sort of jump up in steps of size 1 over n. Sorry, that's hard to read. I have 0 there, I have 1 over n, I have 2 over n, I have 3 over n, and so on and so forth. And at some point, there's going to be the last integer m where m over n is less than a, and then there's going to be the first integer m where m plus 1 over n is bigger than a. So that's all that's happening. I'm sort of walking through the real line using steps of size 1 over n, and all that I'm saying in this inequality is that at some point I hit a, I pass a. And so m is the last step that I took before I passed a. So I'm using the Archimedean property here in two sort of simple ways to zoom in on the region that I'm interested in using the rationals. So let's combine those two properties, and actually that's going to be good enough to get what we want. So by this first inequality here, this one here, a is less than n plus 1 over n. I'm just going to rearrange, that's m over n plus 1 over n. M over n is less than a, so this is less than a plus 1 over n, right? I'm using this inequality here now. And then by definition, using this inequality here, this 1 over n can be replaced by b minus a over 500. And then you sort of stare at it and you go, oh, right, that's less than b, right? So in particular, this is like 0.2% of the way from a to b. And so what have I done? I have an a over here, and I have a b over here, and everything in between, all of these expressions, those are all somewhere between a and b. And then I just have to check, hey, are any of those in Q? And hey, look, this one is. Or I guess this one is the same thing, n plus 1 over n is in Q. And so I found this particular element, n plus 1 over n, which is in Q, and of course, because of this overarching inequality, is also between a and b. And so I'm done, because I found the element. Okay. So this theorem here, that the rationals are dense in R, is one that we're going to be using over and over again throughout the rest of the course. And it's going to be sort of making obsolete a few of the basic theorems that we proved earlier when relating fields and order properties and